Hello, everyone. So we are experiencing some more exciting winter weather. KSU has canceled all in-person activities for tomorrow. That is Tuesday, January 21st. So since we can't meet in person, I decided that a video lecture would probably be the best option for most of you and would give you the most flexibility to be able to do class and manage all of the other things that you're doing. So that's what we are going to do for today's lecture. So today we are going to be covering section 2.6, which is the squeeze theorem and trigonometric limits. And then hopefully we'll get into section 2.7 as well. We certainly won't finish 2.7, but I would like to at least start it that way on Thursday. We can finish 2.7, rock through 2.8, and we will be kind of right back on track. So this week we're covering sections 2.6, 2.7, and 2.8. Those three sections will be due next week, Monday. That is January 27th by midnight. And you will have your first exam, not this coming Thursday, but the following Thursday, January 30th. And so that's going to cover sections 2.2 all the way through 2.8 and including section 2.1. We will be covering section 2.1 next Tuesday on the 28th, and then we will be ready to rock into the exam on Thursday. So the next couple weeks are going to be pretty crazy. So hold on to your hats. Try to keep up. I'm going to be doing virtual office hours tomorrow afternoon on Tuesday the 21st from 2 to 3. So jump in there. Make sure you get your questions answered. Make sure you're using the Open Lab this week and next week and the Smart Center this week and next week. Use those SI sessions that a boss is hosting. Use those resources and make sure you're hanging on. Okay, so without further ado, here we go. So section 2.6, we're going to start with the squeeze theorem, and then we're going to go into some special trigonometric limits. So the squeeze theorem is something that applies in a very specific situation. So we are going to have a function that is always stuck between two other functions. So let's say our function, f of x, is always stuck between these two other functions. I'm going to call L of x, this is my lower function, and I'm going to call u of x, this is my upper function. So no matter which x value we're talking about, f of x is between those two. So what might that look like? What are we talking about here? So I'm just going to say, here is my function f of x, right? This function has to be stuck between some lower function, L of x. And so the lower function needs to be less than or equal to this function everywhere. So it's going to live down here somewhere. We might come back up and they might touch each other occasionally. But other than that, this lower function y equals L of x, that is, can never go above f of x. It's always stuck less than or equal to f of x. And similarly, we have this other function u of x, that's my upper function, that's going to be greater than or equal to f of x everywhere. So again, this is going to live up here. It might come down and touch this in a couple of situations or a couple places, but y equals u of x needs to be greater than or equal to f of x everywhere. It can never drop below. So this is what some of those functions might look like. So let's say we have this function f of x that is stuck between a lower function L and an upper function u. Okay, what would it mean if there was an x value? We're going to say x equals c. This is an x value. And at that x value, I need the limit as x approaches c of my upper function to be the same as the limit as x approaches c of my lower function, right? Those two limits have to exist and be equal, and I'm going to call that limit L. That is the y value that both of these functions approach as x gets closer and closer to c. Okay, so what would that mean? All right, so let's draw this. So I have x equals c. I'm going to put that right here. And I know that I'm going to color code this. Let's see. U is green. So let me come to green, right? So the limit as x approaches c of u of x equals L. So let's say L is my y value over here. That is the y value that u of x approaches as x approaches c. So that means that my upper function, my u of x here, as x approaches c, y has to approach L. And it has to do that on both sides. So it might have to do something like this. I don't know what happens at this point, so I don't know if that point exists or not. We'll make it continuous just because this is our first go at this and we're learning. So I'm going to make sure that that point exists there. It doesn't have to, by the way. We just need the limits to exist. But let's just say this is nice and continuous. The y value is the same as the limit. But notice this function approaches L from both sides, which is what this says. Okay, so that's my u of x function. Okay, and at the same time that that happens, I also need the limit as x approaches c of my lower function L to be this capital L as well. So that means that my lower function is going to live down here, but I know that as x approaches c, y has to approach L. And it has to do that from both sides. So both of my functions are going to come up here and approach L. Again, I'm going to say that point exists here just because it's going to make our brains happier here. But again, there could be a hole there and it's going to be fine because limits don't care about holes. Continuity does, but we're talking about limits here, not continuity. Okay, so what would it mean if these two functions had the same limit? Well, notice since both of my y values have to approach the same value, these two functions basically have to come and basically touch each other there. So what does that mean about f of x? F of x has to be stuck between these two functions everywhere. So, right, it could be over here doing something crazy, but as I approach c, f has to be stuck between these two functions, which means the fact that their limits are the same there forces f of x to also be stuck there, right? These two functions squeeze f of x and they force the limit of f of x to be the same, right? So I need the limit as x approaches c of my function f. It also has to be L because it's stuck between these two functions that squish together and both touch y equals L as x approaches c. Hopefully that makes sense. This is the squeeze theorem. It says if you have, for x not equal to c in some open interval containing c, again, an open interval containing c means that we are going from x equals a to x equals b. We're not including the endpoints. And c is between a and b, but c doesn't have to be included in here. So if L of x is less than or equal to f of x, and f of x is less than or equal to u of x, this says that my function f is stuck between L and u, just like we had up here. And the limit as x approaches c of my lower function L of x is equal to the limit as x approaches c of my upper function u of x. If those two limits are equal and we call that limit L, that means we are in this situation here. Then I know from here that these two functions will squeeze my f of x and force the limit as x approaches c of my function f of x to also be L. This is the squeeze theorem. It says that if your lower function and your upper function have the same limit, it forces your middle function to also have that limit. And this x not equal to c part, basically what that does is if I come back up here and I make this an open circle here, I am still okay. This squeeze theorem still holds because we don't care what happens at C. We care what happens as we get really, really close to C because it's a limit. It's the journey, not the destination. All of these functions still have the same limit. As we approach any of these functions, or as we approach C on any of these functions from the left, they all head toward L, even if there's a hole there. If I approach C from the right on any of these functions, notice they all head toward L, even if there's an open circle there. So whether that point is open or closed doesn't matter. This is going to hold. That's why this is x does not equal c is here. It could be an open circle there. It could be a closed circle. Either way, these two functions are going to squish that middle function and force the limit to be the same there. Okay, so that's what the squeeze theorem says. Now, how do we use it? So the hard thing about the squeeze theorem is that in real life, the stars have to align in order to use the squeeze theorem. Finding a function that's always bigger than a function f of x and finding a function that's always lower than f of x, that's hard enough. But in addition to that, we also need our top and our bottom functions to share the same limit at a certain x value, which is a really difficult thing to do. But sometimes it does happen. We're usually going to see the squeeze theorem with trig functions, and I'll show you why in just a second. Because those guys are bounded, especially sine and cosine, because they're bounded. It's going to make it a little bit easier to find an upper and a lower function. And as long as my limits are the same, it'll bail us out. So let's see how this works. So I want to determine the limit as x approaches 3 pi over 2 of some function f of x. So normally to evaluate a limit, we would take x equals 3 pi over 2 and plug it into my function. But the problem is I don't have a function. I'm not told what f of x is. I don't know what that function is. So I can't just plug it in. So we need to do this a different way. Now, I'm also told here, assuming that -1 is less than or equal to my function f of x, and f of x is less than or equal to sine of x. And that's for all x values from -infinity to infinity. So -1's always less than f of x no matter what x is. F of x is always less than or equal to sine of x no matter what x is. And I'm a bounded function. So with what we had up here, this -1, that is my lower function, L of x, right? Because that's the one that's below my function everywhere. And notice they already set this inequality up. This sine of x, this is my upper function because it's above my function everywhere. Okay, so, well, I don't want to find either of these limits. I want to find the limit as x approaches 3 pi over 2 of f. Well, if we're to use the squeeze theorem, then I'm assuming that my upper function and my lower function are going to squish together and the limits will be the same. But it's not obvious that that's going to happen, so let's test this out and see. So I'm going to take the limit as x approaches c of my lower function here. And so my c value, right, the x value that x is approaching here is 3 pi over 2. That's my c value. So I'm going to take the limit as x approaches 3 pi over 2 of my lower function, L of x, which is -1. What's the limit as x approaches 3 pi over 2 of the function -1? Yep, there's no x to plug in. -1 is always -1, so that's going to be my limit. Limit as x approaches 3 pi over 2 of my lower function is -1. Okay, so let's see what the limit of my upper function is, because if they're the same, right, if they both have that same limit, then it's going to squish my middle function and force it to be the same. So we'll also find the limit as x approaches c of my upper function. And again, my C value is still 3 pi over 2. And my upper function here is the sine of x, so I'm going to take that here. Okay, what's the limit as x approaches 3 pi over 2 of the sine of x? Well, there's an x in here. I'm going to plug that 3 pi over 2 in to evaluate this limit. The sine of 3 pi over 2, this is going to give me a number. You're going to go to your unit circle. The sine of 3 pi over 2 is -1. And notice the limit as x approaches c of your lower function is equal to the limit as x approaches c of your upper function. Because these two are the same, this is going to squeeze my middle function, and I know that the limit as x approaches 3 pi over 2 of my function f of x also has to be -1. I don't even know what that function looks like because it's stuck between these guys and they have the same limit at 3 pi over 2, I know that the limit of my middle function at 3 pi over 2 is also -1. And that is by the squeeze theorem. So that is how you're going to use the squeeze theorem. A lot of times you will have to be given these upper and lower functions because these aren't always very easy to come up with. But sometimes you won't be given those upper and lower functions. Now, the cases where you won't be given those upper and lower functions and you're going to need to find them are going to be with sines and cosines. So I'm going to come back up to this recall in just a minute, but let's just see how this next example is different from the one we just did. This says evaluate the limit as x approaches 0 of x times the sine of 1 over x using the squeeze theorem. Okay, well, if I'm going to use the squeeze theorem, I need an upper function and a lower function, and this problem doesn't give those to me, which is the hard part. So to start creating my upper and my lower functions, we are going to come back to this recall. The sine of x and the cosine of x are bounded functions, right? So sine of x looks like this. And cosine of x looks very similar. It's just like slid sideways a little bit, right? Now, these guys are bounded between y equals 1 and y equals -1, right? They're always stuck. Their y values are always stuck in that little box. Okay, so we don't really need that picture, but for those of you who are visual, I just wanted to make sure that you were clear on where this happens. So the sine of x is always between -1 and 1, and similarly, the cosine of x is between -1 and 1. Now, the cool thing about this is that the sine function is always stuck between -1 and 1, even if you have a lot of stuff in between there. So, for instance, I'm going to write it this way. If you have the sine of some stuff, it is still going to be stuck between -1 and 1. Now, what I mean by that is, what if I had the sine of 3x to the third minus e to the x plus 7? Right? That's a lot of scary stuff inside a sine function. But it doesn't matter what that stuff inside a sine function is. This sine of 3x to the third minus e to the x plus 7, the sine of all of that stuff is still stuck between -1 and 1. Now, if I add anything to the outside of this, if I had like the sine of x plus 1, like if I added something outside, or if I had the sine squared of some stuff, or if I had the x times the sine of some stuff, I would no longer be stuck between -1 and 1. It's just, you can put anything you want to inside a sine function, but if you do things to the outside, the whole function, then these inequalities fail to hold. But you can put any stuff that you want inside that sine function, and it's still stuck between -1 and 1. All right, so I think I'm going to need some space. So I'm going to keep this guy. And the sine of anything is stuck between -1 and 1. That's really what I'm getting at here. I'm going to get rid of this just to give us a little bit more space because I think I'm going to need it. Um, but yeah, that's kind of where we're going to start. So notice I want to know what the limit as x approaches 0 of x times the sine of 1 over x is. And I don't have an upper and a lower function. And notice x times the sine of 1 over x, this entire thing is not stuck between -1 and 1 because I have something happening to the outside of my function. This x kind of ruins it for me. But without the x, the sine of 1 over x, right? The sine of any kind of stuff is stuck between -1 and 1. So no matter what your function looks like, I want you to start with the sine of the stuff that you have inside the sine function. Or if you had a cosine function that looked like, I don't know, 3x squared times the cosine of e to the x plus 2, if this was what you had and this was the thing that you were trying to find the limit of, you would start with the cosine of your stuff is stuck between -1 and 1, right? You take the sine or cosine function, leave whatever is inside it, and bound it between -1 and 1. You can't take any of the other stuff from the outside of the function. You're just going to start with the sine or cosine of whatever you've got. What we have here is the sine of 1 over x. My stuff is 1 over x. Now, because I have stuff stuck inside there, if I ignore that x for a minute, I'm just going to take the sine of my stuff. And because I have the sine of some stuff, I know this is stuck between -1 and 1. So you're going to take the sine or the cosine of your stuff, stick it between -1 and 1. Because those are stuck between -1 and 1. Okay, that's great and all, but I don't need an upper and a lower function for just the sine of 1 over x. I need an upper and lower function for x times the sine of that stuff. Okay, so I want my entire f of x to be in the middle. So now I'm going to multiply or divide or add or subtract whatever I need to make my middle function match the function that I was given. So to make the sine of 1 over x match what I was given here, what do I need to add, subtract, multiply, or divide by? I need to multiply it by an x, right? That's how I'm going to get x times the sine of the stuff. So what I'm going to do is I'm going to multiply by x. But the thing is, I need to multiply by x inside here. And anything that I do to one side of my inequality, I have to do to all of the sides of my inequality to make sure that I don't screw up these inequality symbols, right? So I'm going to multiply by x on every side of my inequality. Addition, subtraction, multiplication, and division, those guys preserve inequalities. We talked about this a little bit, but if you had other functions, if you like took the square root of something, you can't take the square root of everything and still preserve those inequalities. But addition, subtraction, multiplication, and division by anything will preserve them. So we're multiplying everything by x. And so now what you do to one side, you got to do to everything. So -1 times x is -x or -1x. X times the sine of 1 over x is x times the sine of 1 over x. And x times 1 is just x. Now, what I have here in the middle is my f of x function. And notice that I have a lower function now and an upper function. So now, this is my L of x, and this is my U of x. And now I have my inequalities just like I had before. So I'm going to evaluate the limit of all of these things and figure out what they are. So I'm going to clear all of this so that I can actually see the limit that I need. So I'm going to take the limit as x goes to c, which here is 0, of my lower function, which is -x. I'm also going to take the limit as x approaches c, which is 0, of my upper function, which is just x. I'm going to evaluate each of these. The limit as x approaches 0 of negative x is negative 0. Negative 1 times 0 is just 0. And the limit as x approaches 0 of x is just 0. And notice the limit as x approaches c of my lower function and the limit as x approaches c of my upper function is the same, which means it's going to squeeze my middle function f of x, and I know that the limit as x approaches c, which here is 0, of my middle function f of x, which looks like x times the sine of 1 over x, has to have the same limit as both of these, which is 0. Again, this is by the squeeze theorem. So if you're given your inequality, then you just have to find the limits of your upper and lower functions. If they're the same, your middle function will have that same limit. If you are not given upper and lower functions to set up those inequalities, what I want you to do is take the sine of your stuff or the cosine of your stuff that's in your function and stick it between -1 and 1. And then I want you to take everything here and add, subtract, multiply, or divide by whatever you need to do to turn the sine of your stuff or the cosine of your stuff into your entire function f of x. So hopefully that makes sense and you can kind of play with that a little bit. And you can always let me know if that doesn't make sense or how I can clarify that for you. You're always going to start with just the sine of your stuff or the cosine of your stuff, and then add, subtract, multiply, or divide to turn it into the function that you're given. Okay, hopefully that makes sense. All right, so that's the squeeze theorem. That's what it says, and that's how you use it. So now, what if we need some more help? We're going to kind of pivot a little bit, and we're going to go to special trigonometric limits. So these are both in the same section because they tend to be very trigonometric in nature, but the squeeze theorem and these important trig limits are separate. So I kind of want to kind of clear your mind. We're starting something new. These are in the same section, but they're very different. Okay, so now we are going to figure out how to evaluate some trig limits when things let you down. So the way that we're going to do this is we need a couple of important limits that we're just going to be able to use. The first one is going to be the limit as x approaches 0 of the sine of x over x. And the other is the limit as x approaches 0 of 1 minus the cosine of x over x. Okay, well, to start these limits, the first thing that we would do is plug this in, and we would get the sine of 0 over 0. And the sine of 0 is 0. So what we get out of here is an indeterminate form, right? 0 over 0. That says we're at a hole. The limit is still going to exist, but I don't know what it is. And so from your work in section 2.5, you would come back here and you would say, okay, well then I have to algebra the heck out of this. But the problem here is that there is no algebra that's going to get the whole to cancel. And we don't have any trig limits that are, or we don't have any trig identities that are going to bail us out, and we get stuck again here. Okay, so in that case, what you would do is you would go all the way back. This is what we did in section 2.2 and 2.3. So forgive all of my notes in my file structure here. I'm going to come back into our completed notes, and I'm going to go back to what we did in section 2.2 and 2.3. So these are our notes that we did on our second day in class, section 2.2 and 2.3. Notice one of the limits that we did in class is this one. the limit as x approaches 0 of the sine of x over x. Algebra fails us, so what you do from there is you go to your tables, right? So you only go to your tables as a last resort. So you will always go to them in the vertical asymptote situation, but at a whole, you're first going to try all of your algebra and all of your trig tools, but they're all going to fail us here, and so we would go to our tables. Notice from the left, this function went to 1. From the right, this function went to 1. So the limit as x approaches 0. Oh, well, that's from the right. Sorry. They both match, right? So our two-sided limit then is also 1. So we already know what that is. So I'm going to come back. And again, forgive my terrible file structure here with all kinds of stuff in here. And I'm going to come back to what we were working on. And I know, because we just looked and figured it out, this limit was equal to 1. We did that in our notes before. Now, we haven't done this one in our notes, but similarly, algebra is going to fail us here, as will our trig identities. We could make some tables from the left and from the right. You could do that if you really want to, but I'm going to ask you to hit the I believe button for me right here, and that limit will be 0. You will notice that your y values approach 0 from either side. Feel free to make those tables and double check me. But for now, just for the sake of time, I'm going to ask you to hit the I believe button for me. Okay, so these are going to be special important trig limits that we can just use. You won't have to justify these for me from here on out. If you see the limit as x approaches 0 of the sine of x over x, you can just say that equals 1 because it's a special trig limit. One of my colleagues here calls these two trig limits are gifts, right? They're just gifts. We're just handing them to you, and you can just pull them out whenever you want and say, the limit as x approaches 0 of 1 minus cosine of x all over x is 0 because it's a gift that you gave me and I don't have to justify it. I'm just going to pull my gift out and use it whenever I want. So these two limits you can just know and love and have in your brain and just use whenever you need them. And the cool thing about these limits is that it doesn't just work for x. These two things are really placeholders, but to use them, the thing in your sign has to match the thing on the bottom. So really, you can use this and say the limit as x approaches 0 of the sine of any stuff you want over that same stuff equals 1. Right? And so these x's, they could be replaced with anything you want, but the kicker here is that this x on the bottom has to be the same stuff as is up here stuck inside the sign. Similarly, over here, this x and this x could be placeholders, so you can say that the limit as x approaches 0 of 1 minus the cosine of any stuff you want over that same stuff equals 0. But again, the stuff that's stuck inside the cosine, right, the stuff in cosine jail, has to match everything on the bottom. These things need to match exactly to be able to use these. All right. So we are going to be able to use these. These are our gifts. We can pull them out and use them whenever we want. And I also just want to remind you that when we are multiplying with fractions, right, if I have a over c times b over d, we multiply across and get ab over cd. But that's the same as if I reorganize things, right? I could switch the things on the top and just kind of switch these two around, and b over c times a over d is also ab over cd. Similarly, I could super reorganize the things on the bottom, and I could have b over d times a over c, and I'm still going to get ab over cd. I can reorganize this as much as I want as long as the stuff on top stays on top. You can put them on in any order you want as long as the stuff on top stays on top. And as long as the stuff on the bottom stays on the bottom, You can put them in any order you want as long as it stays on the bottom. So that's a cool thing about fractions. If we're multiplying fractions, you can just move stuff around willy-nilly, keep the stuff on the top, keep the stuff on the bottom. So we're going to use that in just a minute. So we want to use our special trig limits to evaluate some of these guys down here. So let's start with number 1. I want to evaluate the limit as h goes to 0 of the sine of 4h over h. And you're going to say, hey, that looks a lot like this one. The limit as h goes to 0, right? I have an h instead of an x, but it's still going to 0 on the bottom. And I have the sine of 4h over h. That looks a lot like this. But the difference is I have a 4h on top and just an h on the bottom. Now, you're going to be really tempted to just take this 4 and pull it out of the sign, but you cannot do that. It is stuck in sign jail. You can't just take it out of the function. It's in jail. Nothing goes in, nothing goes out. So this 4h is stuck inside of my sine function, which means I have the sine of some stuff. And in order to use my gift, I need the sine of my stuff, right? I need the stuff inside my sine function to match the stuff on the bottom in order to use this limit. But the problem is I don't have that same stuff on the bottom, right? I have just an h, but I have a 4h on top. In order to use my limit, I want a 4h down here. Right? If I had a 4h down here, then the stuff on the bottom would match the stuff inside my sine. And then I could just use my gift and say that limit's 1. But I don't have a 4. Okay, so we're going to use what we know about functions and fractions. Sorry, not functions, fractions. And we're just going to multiply by what we need. I have an h and I want 4h, so I'm going to multiply by 4 to get a 4h down here. But again, with fractions, I don't want to change the value. I just want to change what it looks like. So if I multiply by a 4 on the bottom, I have to multiply by a 4 on top so that I don't mess anything up. So I'm going to multiply by 4 over 4. I can do that because it's fraction. Okay, so now what? Now I'm going to multiply across and I'm going to reorganize a little bit. I'm going to use this concept and I'm going to reorganize. So take the journey here with me for just a second. I'm going to show you what I want. I'm going to move this 4 over here so that I have the sine of 4h over 4h because that's what I want. Now the stuff inside my sine matches the stuff on the bottom. That's what I wanted this to look like. But I still have this 4 hanging out on top. So I am just going to leave it over here. And since I moved this 4 over with the h, I just have a 1 down here because I moved the 4 over. And I can do this because I can rearrange. And if I multiply across, notice if I multiply across up here, I get 4 times the sine of 4h over 4h. And if I multiply across up here, I get 4 times the sine of 4h all over 4h. These are both the same. I'm just reorganizing. Now I have the limit of one thing times another thing. If you remember way back when from our limit laws, I can take the limit as h approaches 0 of my first thing times the limit as h approaches 0 of my second thing. You don't have to write this out every time, but your brain might struggle with this sometimes, so I'm just writing this out. If you have the limit of a product, it's the same as the product of their limits, right? Limits work the way that you want them to. You're just going to multiply the limits, and it's going to be fine. The limit as h goes to 0 of the sine of some stuff over that same stuff, that's a gift. That's 1. I can just say that's 1 because, look, it's right here. It's 1. And then I'm going to multiply that by the limit as h goes to 0 of 4. And the limit as h goes to 0 of 4 is just 4. And so the value of this whole thing is 1 times 4. which is 4. That is what the limit as h approaches 0 of the sine of 4h over h is. 4. We just have to reorganize and multiply by a form of 1 to make it look like the sine of some stuff over that same stuff, or 1 minus the cosine of some stuff all over that same stuff that's stuck inside the cosine. All right, so let's try this again. Number 2. I have the limit as h goes to 0 of the sine of h over 9h. Okay, again, we look real similar to this one. So let's see. These don't match, right? The stuff inside my sine and the stuff on the bottom, these don't match, but I want them to match. Now you might say, okay, since I have a 9h on the bottom, I want to make a 9h inside my sine. But remember, this h on the top is stuck in sine jail. Nothing can go in there. Nothing can go out of there. H is stuck in sine jail up here. So I can't just make a 9h inside a sine function on top. So we are going to let whatever is inside our sine function lead the way. So I'm going to kind of reorganize here a little bit. And I want the sine of h, right? I can't mess with what's inside my sine function. Nothing in, nothing out. So I've got the sine of h. So to use these, right, the sine of my stuff has to be all over that same stuff. In order to use this, I just want an h on the bottom, right? Well, I have an h right here, so I'm going to leave that h down here on the bottom because that's what I want, right? I have the sine of some stuff over that same stuff. I could use my gift on this. But that's not everything that I have in my fraction here. So I'm going to reorganize and I'm going to do this and I'm going to pull that 9 out. Notice the 9 is on the bottom. So I'm going to pull the 9 out separately and put my extra stuff over to the side. That 9's on the bottom, so I'm going to leave it on the bottom. I don't have any extra stuff on top, so I'm going to put a 1 up here. And notice this is the same as what I had before, the sine of h over 9h. If I multiplied across, I would get the sine of h over 9h. These two are the same. I just reorganized a little bit. And now I've got the limit of a product. So I can go ahead and take the limit of the first one times the limit of the second one. The limit as h approaches 0 of sine of h over h. It looks just like this. I just have h's instead of x's. So I'm going to use my gift and I'm going to say that limit is 1 times the limit as h goes to 0 of 1/9 is just 1/9. So the limit of this whole thing is 1 times 1/9, which is a 1/9. That is the value of my limit. Okay. And then for this next one, I'm going to kind of go backwards. I'm going to start with 4 and go back to 3. Because 3 is going to be a little more challenging, so I'm going to build up to that. So, number 4, the limit as h approaches pi over 2 of the sine of h over h. And you're going to say, oh, the sine of h over h. That looks just like this, right? The sine of h over h, the stuff inside my sine matches the stuff on the bottom. This looks great. So I can just use my gift and say this is 1, right? No, it's not. It's not 1, guys. Why isn't it 1? Why can't I just use my gift here and say it's 1? Well, because to use my gift, I need the limit as x approaches 0 of that fraction to be 1. Notice this is not 0. Sad face. That's not 0. I can't just use my gift on this because this limit doesn't match this one exactly. So my gift doesn't apply here. So if I can't just use my gift, what do I do? Yeah, we're going to evaluate this limit. How do you evaluate this limit? If I had given this problem to you, way back a few weeks ago, what would you have done? You would plug in pi over 2. This is going to be the sine of pi over 2 all over pi over 2. And you are going to get the sine of pi over 2. That's 1 over pi over 2. To divide by fractions, you're going to keep the top. You are going to change the division to multiplication, and you are going to flip the bottom, right? We keep this. We change the division to multiplication. You flip the bottom. And so you're going to flip the bottom. We're going to multiply by the reciprocal of pi over 2. We're going to multiply by 2 over pi. And when we multiply across, we get 2 over pi. That is the value of this limit. So just be careful. Not only do we need the stuff inside my sine or my cosine function to match the stuff on the bottom, we also need the limit to be just right. As h goes to 0 or x goes to 0, whatever our variable is. Okay, so now let's go to the scary one. The limit as h approaches 0 of the tangent of 3h over 7h. Yeah, this isn't either of our special limits. There's no sines or cosines in here. So we are going to do what we always do, and we're going to evaluate this limit. First line of defense is plugging it in. So I'm going to plug it in. I'm going to get the tangent of 3 times 0, which is 0, over 7 times 0, which is 0. And what's the tangent of 0? Yeah, it's 0. Okay, so I'm at a hole. I am at an indeterminate form. I need to come back and I need to algebra my heart out, right? That's what we learned in section 2.5. We're not just going to lose that training that we have. We're going to follow that training. We're not going to panic. We're going to follow our training. So we're going to come back here and we are going to algebra our hearts out. Do we have any algebra that we can do? Anything from that toolbox that I gave you in section 2.5 that applies here? Yeah, we have some trig identities. What trig identities do you see in here? What would apply to this problem? Yes, the tangent of 3h, I can rewrite that as sine over cosine, right? Tangent is sine over cosine. So I am going to rewrite this. Again, be careful with your notation here. We're going to rewrite that limit as h approaches 0 at every step. The tangent of 3h is the sine of 3h over the cosine of 3h all over 7h. Well, that looks gross. So since we've got fractions within fractions, I'm going to keep change flip. This was my big division bar in my main problem. That division bar is right above the 7h, which is here. This is my main division bar. This is the one that I'm going to change to multiplication. So I'm going to keep the thing on top, and I'm going to flip the thing on the bottom. So this becomes the limit as h goes to 0 of the sine of 3h over the cosine of 3h times, I'm changing that division to multiplication, and I'm going to flip the bottom. This is a hard thing to make your brain do. 7h is 7h over 1, so when you flip it, you get 1 over 7h. Make sure your brain flips it. Okay, so we changed, we flipped, and now we're stuck. I don't have anything else that I can do. So now, what do we got? Well, I've got a sine of 3h on the top. That looks a lot kind of like what I had here in number 1, right? I've got the sine of some stuff on top. And notice I've got other stuff happening in this problem, but I'm not going to panic. I'm going to reorganize, right? Because I'm going to use, for multiplying fractions, we can reorganize however we want. So I have the sine of 3h here. And I want a 3h on the bottom, right? Now this 3h is stuck in cosine jail. I can't just pull it out. I can't just move it. It's stuck in cosine jail. I don't want the cosine on the bottom of this. It's freaking me out. So I'm going to put it over here with my extra stuff. This is the cosine of 3h over here. I don't want it with the sign because notice if I'm going to use my gifts, I want this by itself. Okay, and now I have a 7 and an h over here. So to use my gifts, I want a 3h down here. I want this to be 3h, right? Because I want it to match what's in here. I don't have a 3h that's not stuck in sign jail that I can move around. But notice I have an h. I don't have the 3, but I have an h. So I'm going to put that h here because I'm going to want one there. And this 7, I don't want down here. I'm going to put it over here with my extra stuff. It was on the bottom, so I'm going to put it on the bottom with my extra stuff. I don't have any other extra stuff up here, so I'm going to leave that as a 1. And notice from here, to get my sine of some stuff over that same stuff, what do I have to do? I need a 3 on the bottom, which means I have to multiply by a 3 on the bottom, but whatever you do to the bottom, you have to do to the top. And I can reorganize. I'm going to put this 3 down here with the h to match that. I'm going to put this 3 up here with my extra stuff because it's extra. I don't want it in that first part because I want to keep that with just my gift. So this is going to be the limit as h goes to 0. I'm sorry that this is running into the next problem. I should have had more space there. I'm going to have the sine of 3h over 3h because I'm putting this 3 with this h on the bottom. And I'm going to put this top 3 with my extra stuff over here. 3 times 1 is just 3. And on the bottom, I've got 7 times the cosine of 3h. I just reorganized because my brain likes the 7 out in front. You can leave it on the end. It doesn't matter where you put it. And now I've got the limit of one thing times another thing. I'm going to take the limit of the first thing times the limit of the second thing. The limit as h goes to 0 of the sine of 3h over 3h. Our gift says that is just 1. I'm going to multiply that by the limit as h goes to 0 of 3 over 7 times the cosine of 3h. That's going to be 3 over 7 times the cosine of 3 times 0, which is just 0. What's the cosine of 0? Yeah, it's 1. So this is 3 over 7 times 1. It's 3/7. 1 times 3/7 is 3/7. Now you might be asking me, Susan, there's a cosine of 3h in here. Don't I need to come back up and use my gift with the cosine in it for that? And the answer is no. No, actually, we don't. Because notice in my gift, I need a 1 minus cosine of x to use this. I don't have 1 minus cosine of some stuff. I just have the cosine of the stuff by itself, so I can't use my gift on that. Which means if I can't use my gift on it, I'm just going to put everything I need for my gift in one. Anything else goes in another. I don't have a 1 minus cosine. It can't be part of a gift. It goes in my extra stuff off to the side. All right, that's the hardest one that we had to do in this whole thing. So we got to do 2 more to kind of wrap this up, but I promise these next 2 aren't going to be as hard and complicated as that last one just was. That was the hardest one that we had to do here. I know that number 5 looks extra scary, but again, don't panic. We are going to look at this. And you might say, okay, well, first of all, let's plug it in, right? Because with limits, our first line of defense is to plug it in. If you were on a test and you saw this, you might not see a gift hanging out in there. So we are going to plug it in like we always do. And we are going to get the square root of 1 plus 0 times the sine of 0 all over 2 times 0. The square root of 1 is just 1. Sine of 0 is 0. 1 times 0 is 0. And on the bottom, 2 times 0 is 0. So again, we're stuck. We're in a hole. We're in an indeterminate form. We're going to come back here and we're going to algebra our hearts out. Now, the algebra is going to kind of fail us here because I don't really have addition or subtraction inside a fraction. I know there's addition happening in here, but that addition is happening in a square root that's part of multiplication. That's not something that's being added or subtracted in a fraction. That thing is being multiplied by something. So a conjugate's not going to bail me out. I don't have any factoring. I don't have any trig identities. I'm stuck. So I have a sine function in there, which means it could be a gift. So I'm going to look and say, do I have the makings of a gift up here? Well, I have a sine of h on the top. So I might have a gift hidden in here. So what we're going to do is we're going to reorganize and see if I can, everything in here is connected by multiplication, so I can reorganize. So I'm going to reorganize and see if I can find a gift in here somewhere. I'm going to put my gift first, and I'm going to put everything else off to the side. This is my extra stuff. Anything that's not part of my gift is part of my extra stuff. So this square root on the top, that is definitely not part of my gift. I'm putting it over here in my extra stuff. Okay, so now we have to deal with the bottom part. So now that I have this sort of separated out into my gift and my extra stuff, if I'm going to use my gift, I need the stuff inside my trig function, inside my sine, to match the stuff on the bottom. So what do I need on the bottom to finish my gift here? I would need an h. Do I have an h on the bottom up here? Yes, actually, I do. I have an H down there, so I'm going to put it over here with my gift because that's going to finish off my gift. But that's not the only thing that I have down here. I've got this 2. I don't want the 2 as part of my gift because that would wreck the whole thing. So I'm going to take 2. I don't want it with my gift. I'm going to put it with my extra stuff. The 2's on the bottom, so it's going to go on the bottom in my extra stuff. Right? Gift times extra stuff. That's how we did this with all of these other ones. We're organizing it into a gift fraction and an extra stuff fraction. And so now that I've reorganized, I don't need to do anything else. I don't have to multiply by a form of 1 because I have my gift exactly the way that I want it to look. I've got the stuff inside my sine function, matches my stuff on the bottom. This gift is ready to go. And so I'm just going to evaluate this. I'm going to say the limit of the sine of h over h is 1 because it's a gift, times the limit as h goes to 0 of my extra stuff. Well, the limit as h goes to 0 of my extra stuff is the square root of 1 plus 0 all over 2. Oh, sorry. This should have been an h. Sorry. I should have kept, these should all be h's. I'm sorry. I just noticed that. If you noticed that before and it was bugging you, I'm sorry. That was a typo. All of my variables should be the same here. I didn't mean to mess with you there. They should all be h's. So if you were like, why is she plugging a 0 in for an x when it should only go in for h? Yeah, that's a typo. I'm sorry if that confused you. Pretend that that was an h all along, and then it'll all make sense. Sorry about that. Okay, so now that I've fixed it, hopefully this all makes way more sense. And so now we have the limit as h goes to 0 of 1 plus h becoming 1 plus 0 on top, and I still have that 2 on the bottom. So I've got 1 times the square root of 1 is just 1 over 2. This is just 1/2. That is the value of this big, scary limit, which didn't actually turn out to be that scary. We just needed to reorganize. Make your gift, make everything else. All right, and then the last one, we're going to do number 6 here. The limit as h goes to 0 of 1 minus the cosine of 5h all over h. Okay. Again, you could plug h equals 0 in if you wanted to. You would get 1 minus the cosine of 0 all over 0. And since the cosine of 0 is 1, we've got 1 minus 1, which is 0 on top over 0 on the bottom. We're stuck. And again, algebra is going to fail us. You could use a conjugate here, but no magic is going to happen from that conjugate. You're welcome to try, but the conjugate's not going to be magical for us here. It's going to kind of let us down. And I don't have any good trig identities that's going to bail me out. So we're going to look up here. I know that we've kind of been focusing on the sine one, but take a look at the other gift that we have over here. And what we have looks a lot like that. Trying to get that all on the same page here if I can. It doesn't want to stay zoomed out for me, sorry. But I've got 1 minus the cosine of 5h. So here I've got stuff, right? So I've got a 5h here. I could use my gift if the stuff on the bottom matched the stuff in my cosine, right? So if this matched the stuff inside my cosine, I could use my gift, right? It's that red one. Okay, well, again, I can't put anything inside, into, or out of a cosine function. That 5h is in cosine jail. I can't move it. So I have to make the bottom match the 5h. How do I do that? Right, you are going to multiply by 5, because if I multiply h by 5, I would get a 5h on the bottom. But this is fractions. You can't just multiply by the bottom by something. You got to multiply by the top by that same thing so that I don't actually change the value of this. I just make it look different. So I'm going to multiply by 5 over 5, and now is where I rearrange. Again, I'm going to make a gift fraction and then an everything else fraction right next to it. So I'm going to have the limit as h goes to 0. I'm going to have 1 minus the cosine of 5h. All right, I'm going to try to move this, kind of separate this out to give me a little bit more space. There we go. I'm going to have 1 minus the cosine of 5h. Right, that's the top of my gift. And this 5 right here, I don't want that to be part of my gift. I don't want an extra 5 in here. So I'm going to put it over here with my extra stuff because I don't want it. It's not part of my gift. I don't want it. So that's everything on top I have organized. And then on the bottom, I have an h and a 5. I want both of them over here as part of my gift to make sure that what is in here matches what is down here. Now these match. This is going to be a gift, and both my 5 and my h went over here. I don't have anything left on the bottom, so I'm just going to put a 1 in my extra stuff because I don't have anything else left. And now if I'm doing the limit of a product, I'm going to do the limit of the first thing times the limit of the second thing. The limit as h goes to 0 of 1 minus the cosine of some stuff over that same stuff. Notice this is going to 0. This stuff matches this stuff. I can use a gift. That limit is 0 this time. It's not 1 anymore. The cosine limit is 0 times the limit as h goes to 0 of 5 is just 5, and 0 times 5 is 0. So that is the limit that I get out from number 6 here. Okay, so hopefully that makes sense. We are going to use these special limits, right? I'm calling them our gifts, but these are our important trig limits. You can just memorize these and use these, but you will have to memorize these because I don't give them to you on an exam. So you are going to have to memorize those if you want to use them. And so if you get stuck, this is where I want you to go when you have trig limits and you have these gifts hidden inside your problems. So you're going to multiply by forms of 1 and you're going to reorganize. Put everything into a gift fraction and an extra stuff fraction. And then you'll take the limit of your gift times the limit of your extra stuff, and it's going to be okay. All right, so give that a go in section 2.6. That was section 2.6, the squeeze theorem and our trigonometric limits. All right, so that's section 2.6. I just lost it, 2.6. And then we are also going to move into section 2.7, just to make sure that we have enough time to get through everything this week that we need to, and next week so that we're prepared for our exam next Thursday, and that we have time. I'm hoping that we can take a little bit of class time to review, but it's really hard to squeeze a review into Calc 1, especially on a Tuesday, Thursday schedule. So I'm going to keep rocking to make sure that we get through everything this week. So that was section 2.6. And now we are going to rock into section 2.7. Okay, so section 2.7 is limits at infinity. Okay. So we just did trig for a while. If you need your brain break, pause, take your 3 to 5 minute break. If we were in class, this is where I would give you your chance to shake it out and then come back. So if you need to do that, go for it. Otherwise, we're going to rock into section 2.7. And this is very different. We are done with the trig limits for now, and now we're starting something new. Limits at infinity. So when we are talking about limits at infinity, what we're talking about is we want limits where x is heading toward infinity and negative infinity. We've seen limits where we take x approaching a number and what we get out of that limit is infinity or negative infinity. But what's different here is that our x value, that is the thing that's heading toward infinity or negative infinity. Now, if we were going to do that, I've got a function here, right? This red thing is y equals f of x. That's the function that's graphed here. I want to know what the limit as x approaches negative infinity of this function is. Well, to do that, I would have to figure out where I'm looking at. The limit as x approaches negative infinity. Where would x approach negative infinity? Where would an x value of negative infinity be? Yeah, it would be like way over here, wouldn't it? X equals negative infinity is way over here, which means x is approaching negative infinity. I'm going all the way off my graph and I'm heading off toward the left. This is saying, where do my y values go as x runs off to the left? Okay, so I'm going to follow this function toward the left here. Where is it going? Well, it looks like this function is leveling off, and I would say we have a horizontal asymptote here. It's not written in, but it certainly looks like that. So I'm going to tell you, we have a horizontal asymptote here. That horizontal asymptote is at y equals, what is that? 1, 2, 3. I have a horizontal asymptote at y equals 3. So as x goes off to the left here, my function is going to get closer and closer and closer and closer and closer and closer and closer to y equals 3. It's never going to get there, but that's where the road is headed. It's the journey, not the destination. The road is heading for 3. This limit is 3. Because as x goes to negative infinity, way off to the left, y is headed toward 3. Cool. So now what does this one say then? This is asking the limit as x approaches positive infinity this time of my function. Okay, where would x approach positive infinity? Where would an x value of positive infinity be? Yeah, it would be like way over here. So if I'm taking the limit as x is approaching positive infinity, x is headed way this way. And so I'm going to follow my function off to the right, and I'm going to say, as I go all the way to the right and I follow this function to the right forever. Where's y headed? You're right. Y is taking a nosedive down to negative infinity. So this is what we're talking about. Limits at infinity. X itself is headed to positive or negative infinity. We are looking at the ends of our graph. We call this end behavior. You've probably seen this in a previous class. If you've taken 1111 or 1113, that's college algebra or pre-calculus here at KSU, you have certainly seen end behavior before. So if you don't quite remember that, don't worry. We are going to get into exactly how to do that. But before, I want to kind of come back to this and notice we had a limit at infinity, right? And it indicated a horizontal asymptote for us because notice this horizontal asymptote was y equals 3, and that horizontal asymptote was basically what helped create this limit. And so limits at infinity, limits at your end behavior can tell you whether or not you have a horizontal asymptote, because horizontal asymptotes come from end behavior. They are only asymptotes at the ends of our graph where x is really big or x is really small. They are not asymptotes in the middle. So if a function f of x has a horizontal asymptote like this one did, then either, and let's say our function has a horizontal asymptote. I'm going to go a little further here and say at y equals, I'm going to put that number L in there, right? If f of x has a horizontal asymptote at y equals L, then either the limit as x approaches infinity of my function is L, or the limit as x approaches negative infinity of my function is L. Both sides could approach L. It could be an and here. The limit from the left and the right could both be L, and it would still be y equals L would be a horizontal asymptote for you. But even if just one is, so like here at this graph up here, notice the limit as x went to negative infinity of my function was 3. So y equals 3 is an asymptote, even though the other side wasn't also 3. As long as one of these limits is a number, y equals a number, that's a horizontal asymptote. So if either the limit as x goes to infinity or negative infinity gives you a number, then y equals that number is a horizontal asymptote. That's how you know you have a horizontal asymptote. So if your function has no horizontal asymptote, then both the limit as x approaches infinity of your function and the limit as x approaches negative infinity, sorry, I missed a negative, of your function must be infinity or negative infinity. So the only way to know that you don't have a horizontal asymptote is if both of your ends go to infinity or negative infinity. You can't get a number out. Because if either of these limits give you a number, right, if it gives you some number L, then y equals L is a horizontal asymptote. So the only way to have no horizontal asymptotes is if both of those limits give you infinity or negative infinity. Okay, so we're going to evaluate some limits here, and we're going to figure out if any of these indicate that we have horizontal asymptotes. So let's start with this one. Number one, the limit as x goes to infinity of e to the x. E to the x, if only we knew what that looked like. You should know what that looks like. It's a back pocket function. What does y equals e to the x look like? I think graphs are the easiest way to do that because this is a back pocket function and you should know what this looks like. It is an increasing function. It increases from left to right and it looks like this. And this thing does have a horizontal asymptote right here at y equals 0. But we are going to figure that out with calculus here in a minute. So this says the limit as x approaches infinity of this function. Okay, x is approaching positive infinity. Positive infinity is over here, so we are headed to the right. What's the limit as x approaches positive infinity? As we trace this graph to the right, where's y headed? As we follow this thing all the way to the right. Yep, it's heading toward infinity. Okay, well, since that was infinity, it's not a number, so that does not indicate a horizontal asymptote for me. But in order to say that this function, e to the x, does not have a horizontal asymptote, I need both of these limits to be infinite. So let's check the other side. The limit as x goes to negative infinity of this function. Okay, x is approaching negative infinity. Well, a negative infinity x value would be over here. So I'm headed toward negative infinity. I'm going off to the left. As I trace my function all the way off to the left, where's my y? Where are my y values headed? Well, they're getting smaller and smaller and smaller. They're getting really, 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 really close to y equals 0. They're never actually getting there, but that is where the road is headed. It's headed toward y equals 0. And because I have the limit as x approaches negative infinity of my function and I get a number out, right? I am in this situation. That means y equals L is a horizontal asymptote. So as soon as one of these functions, as one of these limits gives you a number, y equals that number is a horizontal asymptote. Cool. So let's try ln. The limit as x approaches infinity of the natural log of x. Ugh, what does this one look like? ln x. This is a back pocket function. We know what this looks like. ln x, it looks like this. And this is going to keep going up. Okay. So this is what y equals ln x looks like. It's a back pocket function. You should know what that looks like. So what's the limit as x approaches infinity of this function? Well, x equals infinity is way over here, so we're following this function to the right. As we follow this function to the right, where is it going? And I know this kind of looks like it levels off, but this actually never completely levels off. It keeps climbing and keeps climbing and keeps climbing. It just does it really, really slowly. So as x goes to infinity, where's y going? Yep, also to infinity. Okay, so that doesn't indicate a horizontal asymptote, but to be sure it doesn't have one, we got to check the other side. So let's come here and notice this one doesn't go to negative infinity here because ln x doesn't go all the way to negative infinity, right? ln x stops at 0. You can't plug 0 into a natural log. You can't plug a negative into a natural log. So 0 is kind of like the end of the line. So normally we would go all the way to negative infinity. But 0 is where this stops. So kind of the end of the line here is 0. So I know this is a little bit different than usual, but we're going to the left side of my graph. And so as x goes to 0 from the right, 0 is here. We're approaching 0 from the right. I'm going to follow my function that way, and my y values are headed toward negative infinity. And since the right and left sides of my graph, I know this is 0 instead of negative infinity, but we checked both the right and the left sides of my graph, and this indicates that there is no horizontal asymptote because both ends of my graph were infinite. Now, normally we would go all the way to negative infinity. This was a special case, and I'm sorry if that's confusing. This will be the only one that we do where it doesn't go all the way to 0 when we're kind of working with these guys. Okay, so that's what an infinite limit at infinity is. It's as x goes to infinity or negative infinity. And now we know graphically what that looks like. We are looking way off to the right as x goes to positive infinity, or way off to the left as x goes to negative infinity. Now, how do we find end behavior in polynomial rational functions? How do we figure out what polynomials and rational functions do as x gets really, really big or really, really big negatively? Okay. End behavior of polynomials, you're going to look at leading terms. And actually, hold on, sorry. Let me erase all of this. I'm going to kind of rephrase this. So for polynomials, you're going to look at leading terms. Okay. Leading term is how we figured out what a polynomial does. Remind me what a leading term means. It's been a while since we've done this. We're going to look at leading terms. What the heck is a leading term? A leading term is the term with the highest power of x. Not necessarily the one that comes first. It's the one with the highest power of your variable. A term, just if it's been a while, a term is basically anything that's connected by addition or subtraction. So you're going to take the entire part that's separated by addition or subtraction. You're going to take the number part. You're going to take the variable part, but you're going to take the one with the highest power of x. And with polynomials, those leading terms are going to tell you where the whole thing goes. So we're just going to do 1 and 2 here. These are our polynomials. And then I think we are going to, actually, no, we're gonna do all of these, and then we'll do rational functions. Okay. So polynomials, we look at the leading terms. So the reason that we look at leading terms is because as x goes to positive or negative infinity, the highest power of x is going to kind of take over. So our brains work best with positive. So I'm going to look at number 2 first. Now, x is a huge number. It's going to think 3 million, right? X is 3 million. It's a huge number. If I take 3 million to the second power, 3 million times 3 million is huge, right? So this is a giant number. But then look at this one. If I take 3 million to the third power, 3 million times 3 million times 3 million, that number is going to be so much bigger that even if I add or subtract this number to it, this one doesn't even touch it. This number just gets so, so big. Those exponents on huge numbers just take over and nothing else can touch it. So I like to call the leading terms the biggest bully on the playground. They are going to tell us where the rest to kind of push everybody around. So if I look at this 5x squared minus 4x to the third plus x minus 9, who's the biggest bully on the playground? What's the highest power of x here? Highest power of x is that 3. And so I'm going to take the whole term, the things that are separated by addition or subtraction. I'm going to take the entire thing, number and variable, and take the sign with it. So negative 4x to the third, that is our leading term. This is the biggest bully on the playground. It's going to tell us where everybody else needs to go. So we just need to figure out what happens to negative 4 times x to the third as x goes to infinity. Okay, as x goes to infinity, it's a huge positive number. So I'm just going to think, what if I plugged a huge positive number in for x? What would come out? Well, I'm going to take negative 4 and I'm going to multiply by that huge positive number to the third power, right? And again, I'm just putting a plus with a circle here. This is a huge positive number, 3 million. So take 3 million and raise it to the third power, because order of operations say I need to do the exponent before I multiply by that negative 4. So what is 3 million to the third power? It is something ginormous, right? It is a huge positive number, right? A positive times a huge positive times a huge positive. It is an even huger positive number. So I'm going to get an even huger positive number out of that. And now I have to take that even huger positive number and multiply by -4. So if I take a huge positive number and multiply by -4, what comes out of that? A huge negative number, right? Because if I take -4 times a huge positive, I get a gigantic negative number. So since my leading term is a huge negative number, that means the limit as x goes to infinity of this thing is -infinity. That's what the value of this limit is going to be. Because the biggest bully on the playground pulls everybody to a giant negative number. It is pulling this entire polynomial to -infinity. We're just going to plug that number in and see what happens. Okay, so let's come to this one. We're going to come back to number 1 here. What happens if I do a negative number? Again, with this is a polynomial, we're going to look at the leading term, the thing with the highest power of x. Highest power of x here is still -4x to the third. That's the highest power of x. And so I'm just going to say, okay, well, x is heading toward -infinity. It is a huge negative number. I'm going to plug it into my leading term and see what happens. So x is a huge negative number. So when I plug that in for x, I'm going to take that huge negative number and I'm going to raise it to the third power. What do I get when I take a huge negative number and I raise it to the third power? I'm going to have a huge negative times a huge negative, which will give me a huge positive. And then I have to multiply that by a huge negative again. I'm going to get a huge negative out of that. And then after I get that huge negative, I have to multiply by -4. When I take a huge negative and multiply by -4, what comes out? Yep, a negative times a negative gives me a huge positive number. That's what's going to come out of this. So the limit as x goes to -infinity of this entire thing is going to be positive infinity. You can just write infinity or you can write positive infinity, whatever your brain likes best. But this limit up here is going to be positive infinity. This limit up here is going to be -infinity because our leading terms told us where the entire thing went. We just have to figure out what that leading term does as x is hugely positive or hugely negative. You're going to look at your leading term and see where it goes. Okay, how about rational numbers? A rational number is a fraction, right? We've been working with those, something like this, where we have a polynomial on top and a polynomial on the bottom. Well, because we've got polynomials on the top and the bottom, leading terms tell us what happened with polynomials. Now with rationals, we just have to be careful because I have a leading term on the top and a leading term on the bottom, and they're going to fight with each other. So what we're going to do is we're going to do the leading term on top over the leading term on the bottom, and we're going to see where that goes. So we're going to look at that whole thing. So let's come to number 3. The limit as x approaches -infinity of all of this is going to be the limit as x approaches -infinity of the leading term on top over the leading term on the bottom. So what's the leading term on top? Yep, it's 20x squared. That's the biggest bully on top. Who's the biggest bully on the bottom? Yep, it is -4x to the 5th. These two guys are going to take over. Now I just have to compare these bullies and see who's going to win between these two, because now they're fighting with each other. I've got a bully on top and the bully on the bottom, and I don't know who wins. So the way that we tell who wins is that we actually do the algebra here and we simplify this. So let's simplify that. So I'm going to have the limit as x approaches -infinity. 20 over -4, that gives me -5. X squared over x to the 5th. I've got 2 x's on top and 5 on the bottom. Both of the x's on top will cancel with two x's on the bottom, and I'll still have three x's left on the bottom. So this simplifies to negative 5 over x to the third. Now, I have the limit as x approaches negative infinity of negative 5 over x to the third, and I need to figure out where this goes. Again, x is approaching negative infinity, so I'm going to have negative 5 over a huge negative number to the third power. Negative 5 divided by a huge negative, oh, sorry, well, first of all, I'm going to do the negative on the bottom to the third power. I have to do that exponent first. So what is a huge negative number to the third power? Negative times a negative times a negative gives me a huge negative number. What's negative 5 divided by a huge negative number? Well, I'm not sure. So let's see. Hopefully I have a calculator app on here somewhere. If not, I can just use, where's my calculator app? Right? You'd think there would be one on here. Yeah, I don't see one. Yep, no calculator. Okay, so let's go to, we will just use Google. And so I'm going to say, all right, I'm going to have negative 5. And I'm going to divide negative 5 by a huge negative number, negative 1,000. I get 0.005. What if I take negative 5? Oops. Negative 5, and I divide by an even bigger number, negative 5,2,0,0,0,0,0,0,0. Even bigger number. I get 9.615 times 10 to the negative ninth. That means I need to move this decimal point 9 places to the left. I'm going to have 0.8096. So basically what's happening is negative 5, I went a little too far here, negative 5 divided by negative 5,212. Something bigger. Still just a lot of zeros. So basically what's happening is I'm getting positive numbers, but they're really small. Negative 5 divided by negative 1 million. Right, look at all those zeros. I keep getting more and more zeros. I'm getting a positive number out, but they're tiny. What's happening is that this heading toward 0. A negative divided by a negative is a positive, so I'm getting positive numbers out of this. But a small number divided by a big number gives me 0. And the reason for that is if I take a number, right, a pizza, and I divide it into more and more and more and more pieces, the size of the pieces gets smaller and smaller and smaller until they're so tiny you can't even see them anymore. It basically whittles away to nothing. So this limit is 0. So you started with the leading term on the top and the leading term on the bottom, and take the limit as x goes to infinity or negative infinity of that. Make sure you do the algebra to reduce it first, because if you don't simplify first, you won't be able to evaluate that limit. So simplify it, then evaluate your limit. Now, why can we just look at the leading terms on the top and the bottom? I want to show you the algebra that says why we can do this so that you don't just take my word for it, right? So technically what we're doing here, the limit as x approaches negative infinity. So we're starting with this. A lot of times, if you've taken calculus before, my guess is that you probably started out this way and did the algebra. And if you look at any of the solution screens in Achieve, it's going to show you the long way here. So basically, with algebra, I can multiply the top and the bottom of this fraction by anything I want. Just for funsies, I'm going to multiply the top and the bottom of this by 1 over the highest power of x that appears anywhere in this fraction. The highest power of x that appears anywhere is x to the fifth. So if I multiply both of these by this, what I get is the limit as x approaches negative infinity of 20x squared over x to the fifth minus 3x over x to the fifth all over 4x squared over x to the fifth minus 4, right? The x to the fifths cancel, so I just have 4 plus 5 over x to the fifth. And then basically notice what happens. These two cancel and I get an x to the third here. This cancels here and I get an x to the fourth. This cancels here and I get a third. And we're stuck there. So I get the limit x approaches negative infinity of 20 over x to the third minus 3 over x to the fourth over 4 over x to the third minus 4 plus 5 over x to the fifth. Okay, I'm just rewriting this. And now notice, just like what happened here, if I have a number over a gigantic number, as x goes to negative infinity, a number over a huge number, this is going to go to 0. A number over a huge number goes to 0. A number over a huge number goes to 0. This is just negative 4. And then a number over a huge number goes to 0. So what happens here is that I get 0 minus 0 over 0 minus 4 plus 0. I get 0 over negative 4, which is just 0. Basically, what is happening is that as x goes to infinity, if I do this algebra and I divide out everything here by the highest power of x, the things that are going to lead the way here are going to be your leading term on the bottom and the leading term on the top. I know this leading term on top went to 0 as well, but they won't all do that. The things that will be left that are really going to pull this thing around and won't just disappear right away are going to be your leading terms on the top and the bottom. So I just wanted to show you that because Achieve is going to kind of work through that in some of the solutions. And if you've been through calculus before, you've probably seen that presented that way. I'm not going to make you do this. So I wanted you to see this, but you won't have to do this for me. Yeah, you can leave that in your notes if you like, but you won't have to do that for me. I just wanted you to see it worked through. But the big thing is leading term on the top over leading term on the bottom. This guy is what I want you to use. So we're going to do one more of these and then we'll call it a day. So number 4, I have the limit as x is approaching infinity of this fraction. And again, we're going to leave the limit x goes to infinity. We're going to do the leading term on the top over the leading term on the bottom. Leading term on the top is 20x squared. Leading term on the bottom, negative 4x to the fifth. We're going to simplify that. 20 over negative 4 is negative 5. 2 of the x's on top cancel 2 on the bottom, and I still have 3 left. And now the limit as x goes to infinity of this, I'm going to take a huge positive number and plug it in for x. A huge positive number to the third power is an even huger positive number. Negative 5 divided by a huge positive number. I'm dividing it into more and more and more and more pieces. Those pieces get smaller and smaller and smaller until I can't even see them anymore, and I get a limit of 0 out there. Okay, and something to notice, whether you have a positive or negative huge number on the bottom, it still goes to 0 because I'm cutting this into more and more and more pieces. They just get so tiny and go to 0. And I want to connect this to what we talked about earlier with our horizontal asymptotes. Because when I took these, a limit as x went to negative infinity gave me a number. This says I have a horizontal asymptote at y equals 0, both here. And as x went to positive infinity, this also says a horizontal asymptote at y equals 0. So I wanted to connect that for you. Okay, so that will kind of get you started in section 2.7, which is limits at infinity. So you can go ahead and start 2.7 homework as well. You can start looking at limits as x goes to infinity of polynomials and rational functions. And you can still do your 2.6 homework. So give those a go. Let me know how those go. I'm going to have virtual office hours tomorrow, Tuesday, the 21st, at our normal time from 2 to 3. Hop on. Let me know if you have any questions, and we are going to get you right as rain. And it doesn't have to be questions about this. It can be questions about anything so far. So stay safe, stay warm out there, and I will see you in class on Thursday.